Hello again, welcome to another episode of Journeys to the Ice, the podcast of the Antarctic Research Centre. I'm Matthew Wood. Take a handful of snow from a glacier on the Victoria Land coast of Antarctica, and chances are you're holding much more than just frozen water. Incorporated into this snow will be a host of small particles, invisible to the naked eye, that have been blown onto the glacier surface from a range of source areas during episodes of high wind strength. Julia Bull of the Antarctic Research Centre recently completed her master's thesis on the chemistry of the Evans Piedmont Glacier snowpack. She has demonstrated that elemental chemistry is strongly correlated to observed wind patterns and can therefore be used as a proxy for reconstructing longer-term climate variability from ice cores. Welcome to the show, Jules. Thanks for taking time to talk to us today.
My pleasure.
So first of all, how did you end up getting into Antarctic science, and what would you say was the biggest challenge you faced during your 2 field seasons on the ice?
I actually got my project as part of a summer job position. So I was employed as a field assistant for an ice coring project. And then the following year decided to go back down, do a project with Nancy, who was the main investigator on that first ice core project, and do a master's with her. And the second field season was actually for myself to collect samples. There is definitely a certain challenge to that. The first challenge, I guess, would be the isolation. So the first season I was down, we were approximately 500 kilometres north of Scott Base. And when you're out in the field for over a month, at that distance, you can't return for any sort of comforts of home.
Now, the area where you conducted the field work for your own thesis was the Evans Piedmont Glacier. Could you explain what a Piedmont Glacier is and how it differs from a valley glacier like the Franz Josef Glacier here in New Zealand?
Evans Piedmont Glacier is a very low elevation glacier, so it's situated right on the coastline. So unlike the Franz Josef Glacier, which comes down from the mountains with a significant drop in elevation, Evans Piedmont is more of a dome-shaped glacier. So it was local accumulating snow, which doesn't undergo any of those post-depositional things like when the ice travels, you get mixing of the ice. So that's why we were interested in the site.
One major aspect of your work was to examine how the Evans Piedmont snowpack record has responded to changing wind patterns over the glacier. So one term that you will probably have to explain is katabatic winds. What are these?
Katabatic winds are gravity-driven. Air is cooled next to the ice sheet and it becomes very, very dense. So it flows off the centre of the Antarctic ice sheet, down glaciers off the Antarctic continent and out towards the coast off those high elevation sites. Katabatic winds are particularly strong in Antarctica during winter, and they are unidirectional, so they are only going in one direction. What we were looking for was a chemistry signal of those winds.
And of course, in order to give that signal any useful meaning in terms of time, you have to be able to identify annual layers. So while we're on a roll of explaining jargon terms, could you tell us a bit about hoar horizons? And that's HOAR. For any listeners that might be giggling.
Well, the limitation of any geological record, whether it be ice core or sedimentary record, is how well you can date it. If we can't date a record, we can understand the signals that we see in it, but we can't relate it to anything in terms of time. Hoar horizons develop usually a couple of centimetres below the snow surface during summer. The reason that they develop is that the snowpack is colder than the air temperature, so you have sublimation, which is where you go from a snow phase, so you miss that water transition and you go straight to a gaseous phase. So we're actually losing mass within the snowpack during summer. These hoar horizons develop up to about 3 or 4 centimetres thick. The crystal size in the horizon becomes larger and the snow is less dense. So we're using those horizons to identify summer layers that we can use to date the snowpack record.
So you dug these 4 to 5 metre deep snow pits into the surface of the glacier, dated the profile using hoar horizons and other means, and then you proceeded to sample the snow at regular intervals. And then back in New Zealand in the lab, you measured the concentrations of various elements in each sample. So what kind of information did these elemental concentrations give you?
So in ice core research, it's quite common to measure the major elements such as sodium, magnesium, aluminium. Aluminium, depending on the location, can be trace. But especially at coastal sites, those elements are dominated from a marine source, especially sodium and magnesium. The challenge with this project was to measure elements in trace concentrations, parts per billion, parts per trillion. That includes aluminium, titanium, vanadium, zirconium, an entire array of elements. Interestingly, we were also looking at things like antimony and lead, which are associated with an anthropogenic pollution signal. And we think those sources are coming from places relatively local to Evans, such as Scott Base, McMurdo Station, which is the largest station on the Antarctic continent, the Italian station in Terranova Bay, which is just north of Evans. And then you have all the terrestrial-derived aerosol mineral dusts, and they are aluminium, titanium. Zirconium was a really interesting one because it responded really well to wind transport. So we were trying to identify which elements come from a marine source, a terrestrial source, pollution source, and a volcanic emission source.
These aerosols are, of course, being blown by the wind from their various source areas onto the glacier surface. But your results show that the delivery of aerosols isn't actually constant throughout the year. What were the seasonal differences that you observed?
The chemistry that you see in a snowpack record is going to respond to the transport of the aerosol to that record. Wind speeds are significantly higher along the Victoria Land coast during winter due to the increase of katabatic wind strength, and also cyclonic activity can be stronger during winter as well. There's greater atmospheric vigour. Sure, you get the katabatics coming off the continent transporting mineral dusts, but you also get winds coming across from the south which can transport marine aerosol and any potential pollution signal.
You mentioned katabatic winds transporting mineral dusts off the continent and onto the Evans Piedmont Glacier. But in your work, you refer to other coastal sites around Antarctica that have concentrations of typical mineral dust elements like aluminium and iron that are orders of magnitude lower than at Evans. What makes this part of the Victoria Land coast unique among the Antarctic coastal sites that you compared?
Directly behind Evans Piedmont Glacier is an area known as the McMurdo Dry Valleys and the Transantarctic Mountains. These are some of the most extensive rock and soil outcrops that exist in Antarctica, which of course is mostly covered in ice sheet. The sites I was comparing my study to, they have very limited local mineral dust sources, and the elements that you refer to, aluminium and iron, we think they're mostly derived from mineral dust. So really it's just proximity to the source regions.
The term mineral dusts in this context actually encompasses a large range of minerals that each carry a different combination of elements within their crystal lattice. What control does mineral type have on the relative abundance of some terrestrial source elements compared to others that are only found in trace amounts?
The concentrations of aluminium in Evans Piedmont Glacier snow was at least an order of magnitude higher than, say, concentrations of things like zirconium. Aluminium is bound up in relatively soft minerals such as plagioclase. Conversely, zirconium is mostly in zircons, which are very difficult to transport and also very difficult to erode. So although zircon showed the strongest correlation with wind strength, and I think that is because it really can only be transported when the wind strength is relatively high, aluminium concentration is really a lot higher.
So the terrestrial source area of the McMurdo Dry Valleys and the Transantarctic Mountains will have remained more or less constant in size and shape and position over the annual to decadal timescales of the Evans Piedmont Glacier snowpack record. But the marine source of the Ross Sea presumably undergoes significant seasonal changes. What variables do you need to take into account when considering annual marine source elemental concentrations?
Marine aerosol can be sourced from an open ocean source, so from sort of just sea spray, bubble bursting at the surface. A second way of producing marine aerosol is from the surface of sea ice. All the salty brine that was in the water is often injected up onto the surface of the sea ice. So this is really enriched in sort of marine derived elements, and this forms frost on top of the sea ice surface. So in summer we have a much closer open ocean source. During winter we have more sea ice surface, so we can get a larger production of frost flowers. What the dominant source region of marine aerosol specifically is to Evans is debatable. I think it's both. Marine aerosol from the open ocean are extremely important during summer and probably produce the mean sodium input but those extreme wind events during winter have enough strength to move these frost flowers from the sea ice surface onto Evans Piedmont Glacier. It's also been argued that winter wind strength is strong enough to move marine aerosol from a more distal open ocean source. So it's a hard one, it's still very much under debate, but the strongest correlation that we do get between wind strength and elemental chemistry is between the terrestrial elements, and that really is because the source region remains constant. The marine-derived element sodium is less significantly correlated to wind strength, and I think that is because of this variable source region.
So we've discussed the variations that can be seen in absolute elemental concentrations and what they represent within a single year's accumulation. But to turn now to the interannual record, you've plotted the ratio between certain elemental concentrations over the last decade or so and identified this major shift around the year 2000 to 2001 that is mirrored in the wind record from a nearby weather station. Can you elaborate on this and explain how you've interpreted this shift in relation to climate forcing beyond the Victoria Land coast or even the Ross Sea?
Looking at an elemental ratio, so we used aluminium to sodium, which is a terrestrial element, to a marine-derived element, you get an indication of more mean conditions in wind. And what we saw was that aluminium sodium was related to average summer wind speed. What I think we are seeing in this shift really is a change in the mean state of the atmospheric circulation of the Ross Sea. We've related this change to the El Niño Southern Oscillation, which is a subdecadal climate signal. It's driven by changes in the tropics, but we think this signal is propagated to Antarctica. So a number of records have seen correlation between the Southern Oscillation Index and things like sea level pressure, sea ice extent, all sorts of things. So we think it really is quite a strong signal within the Ross Sea. So during La Niña events, the climate of the Ross Sea is driven mostly by marine cyclonic activity, and we think we get a lot of marine aerosol transported to Evans, so a lot of sodium. Conversely, post-2000, the Southern Oscillation Index is predominantly negative, and we've associated this with a shift in the climate of that region from direct marine air masses to atmospheric circulation, which comes over the West Antarctic ice sheet towards the Victoria Land coast. So it's a more continental signal. The relative input of sodium is decreased, and the aluminium sodium ratio is significantly higher for this time period. This correlation, of course, needs to be confirmed over a much longer time period.
Well, presumably now that you have this finding that the snowpack record elemental chemistry is directly related to wind patterns across the Victoria Land coast, it gives you the tools you'd need in order to interpret longer-term climate records from local ice cores.
Yeah, it does. I mean, that was the main aim of my project, to establish that for the modern day, assume that those relationships remain constant over time, and then to use those in longer-term ice core records. There's been a number of ice cores taken from the southern Victoria coast. There's one at Evans Piedmont itself, which is a 105-metre ice core record, which we think extends back a couple of hundred years, so it's still not long term. But that's what's really interesting about those ice core records, is that they're very high resolution, so we can see annual signals that are related to climate phenomena that might not be recorded elsewhere, where the records are longer but they're not at the same resolution. Our record was 14 years, so we know exactly what was happening with the climate during that time period. In fact, we had an automatic weather station located 10 kilometres away from Evans, which is what we were correlating our chemistry to. So we were wanting to verify the tools we were using were going to be related to real modern day processes.
I think it's amazing that in Antarctica you're seeing this clear response to a climate phenomenon that originates in the tropics. I guess it points to an Earth system that is much more interconnected than many people would assume. Also, today, with climate records being relied upon to provide information about human-induced climate change, any changes that occur from year to year at any one location really have to be interpreted in the context of this natural global climate variability.
I guess the important thing to highlight is this connection between El Niño and the Ross Sea region has been established by a number of previous studies, but the controls on the system are not particularly well understood. And the reason for that is that the meteorological records within the Ross Sea region extend back at most about 50 years, and that's one record from Scott Base. The other automatic weather station records we have are 10, 15-year records at most. And then we've got satellite data from the 1980s. But when you're looking at a cycle of 4 to 5 years and you have, say, a 20-year record with good resolution, it's difficult to establish what the controls are on that cycle and what the relationship really is. So I think it's quite exciting that we can see it in a snowpack record, because that gives us the potential to try and see it in an ice core record, which can go back hundreds of years. It's important that we understand what the natural variability of these climate systems are. During the 1990s, the Victoria Land coast average annual temperature appeared to be cooling. People were saying, oh, well, this is good evidence that global warming actually isn't happening. I mean, this is quite anomalous. Other regions within Antarctica, the peninsula was warming quite rapidly, and recent studies have sort of shown actually that overall mean state conditions in Antarctica has been warming with the rest of the globe. Why the Victoria Land coast specifically was cooling during the 1990s, this has been attributed to an increased negative phase of the Niño Southern Oscillation. So you've got stronger winds coming across the western Antarctic ice sheet, which compared to sort of marine air masses coming in from the Ross Sea is really going to cool the climate. So these mean state changes are quite significant when you're looking at records that are 20 years and trying to determine longer term trends from those. You have to be cautious. So looking at longer term records from ice cores and proxy information is really quite important.
Well, I hear that after looking at snow for over 2 years, you're about to head off to some more snow, this time in the Canadian Rockies for a hard-earned break and some snowboarding. So congratulations on completing your thesis, and thanks very much for your time.
Pleasure. Thank you.
For more journeys to the ice, visit sciblogs.co.nz/journeys to the ice.